guys! Today I thought we'd talk a little bit more about electronegativity trends and kind of what that means in terms of the electrostatic attractions that we've already discussed. So, first of all, what is electronegativity? Electronegativity is what we say is a measure of the tendency of an atom to attract other electrons or electron density toward itself. So the more electronegative something is, the greater a tendency it has to attract other electrons. And when we look at this particular trend on the periodic table, we take note that as you go across a row, electronegativity increases, and it also increases as you go up a column. So henceforth, that's why we kind of have this catty corner little line leading up to fluorine, which is the most electronegative atom on our Pauling scale with a reading of 4.0. So let's talk about, okay, well, why does the trend work this way? Why is fluorine the most electronegative atom? And why does it increase going across a row, but increase going up a column? So just a reminder of what we had talked about last time with our particle nature of our nucleus containing our positively charged protons versus the cloud nature of our electron. So back to electrostatics. We know that for these to be completely satisfied, the positive charge and the negative charge really want to be right on top of each other. But because the nucleus is a particle and our electron is like a cloud, we know that we can't fully make that electron collapse down on top of the nucleus. This is our ideal situation, but unfortunately, we know that the real case is that the two can't be completely on top of each other. So what ends up happening, like last time, is that they're going to seek other electrons, and that's what leads us to bonding. So we know that more electronegative atoms are going to be involved in stronger bonds. They're going to be able to attract and hold on to the electrons of other atoms better. So let's take a look at this trend as we go across the periodic table. So here on the board we're going to take a look at nitrogen, oxygen, and fluorine. So the two atoms before we get to fluorine. So what happens is every time you move one spot over across the row of the periodic table, the atomic number increases by 1. And so we know that that means you're adding one proton and electron pair. So as you go across, each time you're increasing by one proton and one electron. And what happens with that electrostatically, and here we're just representing the p electrons that we've added because they all have two 2s electrons. So as we move from nitrogen to oxygen to fluorine, each time they're adding one more proton and electron pair. And what happens is as they get more electrons, they become more dissatisfied because they see more, and that makes them want even more. Because the more dissatisfied they are, the more they're going to want to search for and attract other electrons. So if we had another electron from an atom coming in, fluorine would be better able to attract it because it's hungrier for more electrons. It's more dissatisfied, so it's going to attract it better. So you might be asking at this point, okay, well, if each time you add a proton and electron pair, dissatisfaction increases, well then, why don't these larger atoms toward the bottom of the periodic table, why aren't they more electronegative? Well, all those electrons can also have another effect that you may have heard referred to as shielding. So let's take a look at iodine, for example. Iodine has an atomic number of 53, meaning it has 53 protons and 53 electrons. But what happens is all these electrons, it has 1s, 2s, 2p, 3d, 4s. So it has lots of layers of electrons. So you have your positively charged nucleus, but it's surrounded by layer upon layer of electrons. And those layers of electrons actually shield the nucleus, and they kind of prevent it from being able to see more electrons. So if an electron from another atom were to come in, all the electrons that iodine already has kind of block iodine from seeing this one. So if it can't see it, you know, how can it attract it and how can it hang on to it? Because all these layers shield our nucleus from seeing incoming electrons. So therefore it doesn't have as great a tendency to attract them and is therefore less electronegative. Another way to think about shielding is using a lamp. I'm going to set up some sheets of paper, and let's just pretend that these sheets of paper represent layers of electrons. You can kind of think of this as being like a paper lantern. Because if you had a paper lantern where you had a light bulb and then had a layer of paper, some light's going to shine through. But if you added more and more layers, each time less light will shine through. Kind of the same with electrons and shielding. So, if we turn on our lamp here, I set that up like that, you can see that with each layer, less and less light passes through. Because just from this one layer, you can see more light in this section than if I were to come all the way over here. So if we think about this being our nucleus containing those positively charged protons, so it's got that positive pulling power to pull those electrons into it. But if it's blocked by all these layers of electrons, if I were to put another electron from an incoming atom all the way over here, it's not going to be able to attract it as well because it's blocked by all those layers. So less of its attracting power is going to be able to reach that particular electron. And so therefore it's going to have a weaker bond when sharing electrons with other atoms. And so to connect this phenomenon to what we're going to learn in the future is that less electronegative atoms are going to make weaker bonds. And so that can lead us to discussions of acidity, because we know that weaker bonds to hydrogen that is, makes for a stronger acid. Alright, so just a couple of things to keep in mind.